Well, hello, and welcome back to Engineering 201 Electrical Fundamentals. And I want to wrap up our work with Thevenin's equivalent circuit and Norton, for that matter. If you take the Thevenin and do a source transformation, you will get a Norton. And work a couple problems, an easy problem and a difficult problem. But before I get into those, I'd like to talk about the schemes that we might use on these. And there's three types of problems. One type of problem is a circuit that has both independent and dependent sources. So it's going to have both independent, those being the voltage sources like this and current sources like this, and then dependent sources, and we have a variety of those, the diamonds, whether that's a voltage source that's controlled by a voltage or a current, or whether that is a current source that's controlled by a current or a voltage. So you have those possibilities, and what you're going to have to do on this is you're going to have to find V open circuit, and you're going to have to find I short circuit, and then with those you can calculate R Thevenin, which is going to be the ratio of the open circuit voltage to the short circuit current. Okay, now what you're hoping for is that you have a circuit that has only independent sources, so you only have the voltage sources like this, or the current sources like this. You don't have any diamonds, so to speak. And what you can do with that is you will find V open circuit, or you really only need to find one or the other, I short circuit. And then to get R Thevenin, what you're going to do is you're going to short the voltage sources. And open the current sources, short voltage sources, open current sources, and then look into the terminals and find R equivalent at the terminals, and that will be your R Thevenin. Now this is obviously quite a bit easier, so people try and force problems from the category 1 into these problems, and that does not work at all. If you have a diamond, you have to do it this long way. And then there's a last one, and we're not going to tackle problems in this, but I'm going to point it out. If you're going into electrical engineering or something like that, you may want to think about this. But what if you have a circuit that has only dependent sources? So maybe it's a circuit that looks like this. It has a diamond. I don't know whether it's a voltage or a current source, and you've got a resistor here and a resistor here, maybe a resistor. What are you going to do? Well, what you actually have to do is you have to put a source on here. So we'll talk about putting a source on here. And maybe we would put a current source on here. And you can just take a current like 1 amp. Okay? And with that, what you will do is you'll find this voltage across here. Hopefully I'm still on screen there. And you can say then that R Thevenin is equal to the open circuit voltage, well, not the open circuit voltage, but really the voltage that you find, divided by 1 amp. Or if you wanted to, I mean, you could also say, if you were to do this, you could put a voltage source across there and find the current through it. So find this current. We could say that this is 1 volt. Okay, there's nothing sacred about 1 amp or 1 volt. Use whatever you want. You could use milliamps or something like that, but you usually just want to pick a value that's easy to work with. 1's pretty easy to work with. So over here you'd get that your R Thevenin is equal to what? The 1 volt divided by whatever you came up with for your current. Okay. So, make sure volts over amps, yeah. And then your model, these two, the model, at least the Thevenin model, whether you're looking at this one or this one, they always come to the same answer. you have your V open circuit, which is your voltage Thevenin, and then you have your R Thevenin. That's what the model looks like. This one, the model is quite a bit different, and maybe we should keep it separate over here. Its model always is just a resistor, R Thevenin. Okay. So like I said, we're not going to, I don't think we've got any homework problems. We definitely won't have anything on a test like this, but it's something to think about. It is a possibility if you have only dependent sources. Now, the other thing to think about is some people will use Thevenin's theorem for circuit simplification, and they'll look at building the Thevenin models to reduce the circuit. I haven't gone into that. I've used it more for a model so that we can figure out maximum power and things like that. But if someone uses Thevenin's theorem as a circuit simplification technique, that's fine. That's fairly standard too. Well, with this at hand, let's see if we can do some problems. Let's say we have a problem like this. And we'd like to find the maximum power transferred at these terminals. We could say A and B. So find maximum power that can be transferred at A and B. So what we're going to do is we're going to come in here and we're going to put a resistor between A and B, and we need to figure out what that resistor is, and then we can come up with that maximum power. Well, if we go back and look at what we just talked about, we have a circuit that doesn't have any diamonds in it, right? I mean, that's worth something in and of itself. People are usually happy with that. No diamonds. So we can use the shortcut on this. This is a shortcut. Okay. We're going to short the voltage sources and open the current sources to find R Thevenin. So that means we only have to find V open circuit or I short circuit. So let's do that. What I'll do then is, let me flip pages on you so this doesn't get too cluttered. We'll come back to page 2. So I'm going to set about finding V open circuit. We could find I short circuit if we wanted to, but I'm going to find V open circuit. So find V open circuit. Well, let's see. How can I do this? Probably mesh might work well here. I'll say that this is I1. I'll say this is I2. There's no current out here because, remember, we're looking for V open circuit. So I could start my equations with what? If I start right there and go around there, I have a gain of 12. So I have minus 12 plus 6k I1 plus 6k I1 minus I2 is equal to 0, right? Which gives me what? 12k I1 minus 6k I2 is equal to 12. Nice equation, but two unknowns, so I got to go find another one. Well, if I go around here, I could say that I have 6k I2 plus 6k I2 minus I1. That's right there. And then I'm going to be coming through this one from positive to negative, so that's a drop. So we'll say that that's positive 3. Gets me back to my starting point, saying that's equal to 0. So I have minus 6k I1 plus 12k I2 is equal to minus 3. So I have a couple equations there, this equation and that equation. And what are we really looking for? Well, over here, V open circuit would be the voltage from there to there plus the voltage from there to there, right? So I could say it's 3 plus, what's this voltage? Well, if I1's going like that, I could say this simply I1 times 6k, right? So the reason for doing that is I don't really need I2. So if I solve this for I1, so I think I'll write this out here. If I multiply this by 2, I'm going to get 24k I1. So multiplying that by 2, 24k I1 minus 12k I2 is equal to 24. And then bringing this one up here, I've got minus 6k I1 plus 12k I2 is equal to minus 3. When I add those together, I'll get rid of the I2s. That's good. And I've got, what, 18k I1 is equal to 21. So I1 turns out to be equal to 21 over 18k. I guess that's good enough. So I'll run that up into here. So we have 3 plus 21 over 18k times 6k. The k's cancel. In fact, I have 21 over 3, which is 7, which gives me what? 10 volts? So that's my V open circuit. Okay, that's my V open circuit. Now I'll come back here to page 2 and maybe record that V open circuit is equal to, what did we say, 10 volts. Okay, and that's from page number 3. So now we could go ahead if we wanted to and find I short circuit. You would short this out, find I short circuit, find the ratio of those, and then come up with R Thevenin. But since it's since there's no diamonds in there, there's no dependent sources, we can use the shortcut. Shortcut to get R Thevenin. Well, what is that shortcut? I short the voltage sources. I open the current sources. Looks like I only have voltage sources, so when I short that one out, I get something like this. And this, and then I short that out. I'm going to have that. And I'm looking then back into these terminals and trying to find the equivalent resistance. This is 6K, this is 6K, and this is 6K. Okay. So, let's see. What is this? Well, you imagine a current. This is a little hard to see. And you could if you wanted to. I mean, you think about going down to lab, and how does this happen down at lab? What we do is we essentially take the ohm meter, and what's that ohm meter do? Well, it takes and puts a small voltage across here, like that. And with that voltage, then it figures out what current is going through here. It takes this known voltage and figures out what current is going through there, or vice versa, puts a current in here and finds the voltage across it, and then that ratio is the resistance. So if you don't like looking at something like this, you could, like we had talked about in that other problem, or conceptually here when we began speaking about this, about putting a known voltage source and finding the current through it, a little different context with the same technique. Take a known voltage source or a known current source and then figure out what the remaining unknown is. So you could do that if you wanted to. I think we can probably get through this a little differently. If you notice, this point and this point and that point are all the same. And likewise, this point here, and that point there are all the same because you have dead shorts between those, right? So with that, I could really say that I have 6K in parallel with 6K in parallel with 6K. Now, if you don't like that reasoning, imagine yourself as some current coming in here. You have the option of going through here, that's 6K, and then you could escape and get out. Or you could go this way. Maybe you're seeking a path of least resistance. Go through that 6K and get out. Or maybe you're real crafty. You come up here. You go like this. You go through this one. And then you get out. Either of those three paths is through a 6K resistor. So they are all in parallel. So we would have 1 over 6K plus 1 over 6k plus 1 over 6k, which gives me what? 2k? Because 6 and 6 is going to be 3, 3 and 6 is 2 when I'm doing parallel. That doesn't sound like good math, but when I'm doing parallel, that's what I get, product over sum. So I get 2k ohms. That's equal to R Thevenin. And again, if you don't like my reasoning here, you could assume some voltage source, put across there, find the current, find the ratio of those when you're done. You'll come up with that same answer. Or if you really don't like this, remember, we don't have to use the shortcut. You could come in here. You could short this out. You could find I short circuit and do it that way too. You don't have to use the shortcut. So some options for you there. Well, let's go back to page number 2. And we've got then that R Thevenin is equal to, what did we say, 2k ohms? Yes, 2k ohms. It should really be k ohms. K ohms. 2k ohms, and that's on page number 4. Okay, so we use the shortcut. We've got that. I mean, we could build the model at this point if we wanted to. There's the model. 2K, right? 2K ohms. So we're asked then, what's the maximum power? Well, the maximum power is going to be when RL is equal to R Thevenin, which is 2K, right? And what value of power are we going to have? Well, if that's true, we would have, what, 5 volts across here? This is where you could remember the equation we talked about when we derived maximum power, but I just remember that the resistances have to be equal. Because they're equal, the voltage split is easy. And I could say then that power is equal to 5 squared divided by 2K, which is 12.5, yeah, 25 over 2, 12.5. Because I have the K in there, I'm going to get milliwatts. Okay, 12.5 milliwatts. Now, I don't know, that said we had to do a Thevenin. We came up with that answer. What if we tried the Norton? Can we get the Norton? Yeah, we should be able to. Let's see, V is equal to IR, so I is equal to V over R. So I take this voltage, I get 10 volts, and I divide by 2 k ohms, which gives me 5 milliamps. So I could say then that the Norton model looks like this. 5 milliamps with the same R Thevenin. Let's see. I don't want to write R Thevenin, I want to put 2 k ohms. So 2 k ohms. How do I get maximum power transfer here? Well, absolutely. Our load, I'm using the eraser a lot here. So RL is going to be equal to R Thevenin, which is equal to 2 k ohms. So if you have 5 milliamps coming up to this point, you have a split. Some of it goes down here and some of it goes here. What's that split going to be? Well, because these resistors are the same, it's very easy. That current right there is going to be 2.5 milliamps, isn't it? So now power is equal to I squared times R. What do we have? 2.5 squared times the resistance of 2K ohms. Gives me what? Double check that with the calculator. I'm pretty sure what it should turn out to be. 12.5 milliwatts. Okay. So hopefully lots of good things we were able to pick up in that problem. You know, probably not going to do both of these unless you're specifically directed to. But I just wanted to show you that that does work out. So. Well, let's see. We started out talking about this. Well, we've done an example for this. I guess we probably better do an example of this one, right? I said we weren't going to necessarily worry too much about this. Again, if you're going into electrical, you might think about things like that. But let's go and look at a more difficult problem. where we have circles and diamonds both, or better said, independent and dependent. I think that is page 4, page 3. Yes, so this should be page 5. So let's say we want to come up with just find R Thevenin. Okay. What is the Thevenin voltage here? Find R Thevenin. So, and obviously if we find R Thevenin, maximum power is very easy to get at. We could come up with a Norton model, we could come up with the Thevenin model, but this is the real key here. And we notice that we have both diamonds, dependent sources, and circles, independent. So we're back here to independent and dependent. So we've got to find both V open circuit and I short circuit. No shortcut here. So no shortcut. No matter how much we wish we could use a shortcut on this, we can't. So we got to grind through finding V open circuit and I short circuit. So let's go about that. I'll come back to this page 5. So we'll say that this is finding V open circuit. Okay, so there it is right there, V open circuit. Well, let's see, I think I'll use node analysis. We'll put a voltage, we'll say this is V1, which is going to be the same as that voltage there. And we've got a current here, IX. Why don't I put a current here? I'll say this is I1. I've got 2IX. We know that this current here is going to be 0, isn't it, if that's open. So I should be able to say that IX plus 2IX is equal to I1. Is that right? IX is going in, 2IX coming up here and going in, because this is all essentially one node up here. 2IX is going in, and then I1 is leaving. So I could say that 3IX is equal to I1. Can I talk about IX? Yeah, I should be able to. I just need to find the voltage opposite that, which is that. It's going to be minus V1 plus 12. So 3 times 12 minus V1 divided by 3 is equal to I1. What's I1? That's going to be V1 divided by 12. So I get 3's cancel. I get 12 minus V1 is equal to V1 over 12. Multiply the whole thing by 12. I get 144 minus 12 V1 is equal to V1. And we could then move this over. 144 is equal to adding 12, so 13. Isn't that right? Yeah, 13 V1. So V1 becomes equal to 144 divided by 13. Okay, which I guess we could keep that as a fraction. I don't think, there's probably not a lot of advantage to that. Yeah, I'll just go ahead and make a decimal. 11.08. So we'll say this is 11.076. And I've got too many significant figures. Since it's an intermediate step, I'll go ahead and keep that. Okay, it's not my final answer yet. Now that's V1. So what's V open circuit? Well, I say that because this current here, I, because I is equal to 0, V open circuit, then, therefore, V open circuit is equal to V1, which would be that 11.076 volts. Okay, does that make sense? Because this current is 0, we know that V is equal to IR. So if the current is equal to 0, you put 0 in there. No matter what this resistance is, the voltage across this thing is equal to 0. So if that voltage is 0, then this voltage here has to be the same as that voltage there, which by definition is V1. Okay, so because this current there is equal to 0, V open circuit is equal to V1, and I have that. So let me summarize that here. V open circuit is equal to 11.076 volts, and that's from page number 6. Okay, so we'll go on to 7. We can't use a shortcut. Got a diamond, no shortcut, so we have to find I short circuit. So find I short circuit. No shortcut. Okay. So what we're going to do is we're going to short this thing out, and we put a designation there, I short circuit. And let's see, why don't I go ahead, I'm going to put some of the same currents that we had in here. We got IX, I'll call this I1. And I won't call that I because we got a name for that, I short circuit. Take this as my reference ground. Take this node, which is again, this whole thing is the same. That will be V1. So I should be able to say that IX plus 2IX is equal to now what? I1 plus I short circuit. Had exactly the same thing as before, but now we've got this I short circuit leaving this node up there. So I'll have that. So I've got then again, just like we did last time, 3IX is equal to I1 plus now the I short circuit here. And we're going to have then 3 times IX. Need to go that way, so that's minus V1 plus 12, 12 minus V1 divided by 3 is equal to I1, which is V1 over 12, plus I short circuit, which would be, well, that's fairly easy, V1 over 12 also, right? So I could say that I have 12 minus V1 is equal to V1 over 12 plus V1 over 12, which would be what? V1 over 6. Multiply everything by 6, and I get what? 72 minus 6 V1 is equal to V1. So V1 is then, or let's see, 72 is equal to, add 6, so I've got 7 V1. So V1 is equal to 72 over 7. Okay. Well, what good is that? Well, right here, I short circuit. We know that I short circuit is V1 over 12. So I short circuit is equal to V1 over 12. So I get 72 over 7 divided by 12. I'm just going to go ahead and evaluate that, which gives me 0.857, and that's amps, not milliamps. Okay. Okay, so I'll put that back here on page number 5. I short circuit is equal to 0.857, 0.857 amps, and that's page number 7. Okay. Did we do that right? Let me double check that. Yeah, 0.857. Good. Okay. So then I should be able to come back with this from page 5, and and take these two, the combination of these, and come up with R Thevenin that's going to be equal to V open circuit divided by I short circuit, which would be 11.076 divided by 0.857. They're both positive. That's good. If one was negative, the other would have to be negative. Let's see. 12.92, I'll just call it 12.9. There's three significant figures. 12.9 ohms. Okay, so we can answer this thing. We can say that R Thevenin is equal to 12.9 ohms. 12.9 ohms. Now, if you wanted to go further, you could use this V open circuit and come up with the Thevenin model. 11.1 volt. And now that we have that, 12.9 ohms. Or you could use this short circuit and come up with a Norton model. .857 amps. And 12.9 ohms. And remember that the only difference between the Norton and the Thevenin is a source transformation. If you take this 11.1 volts and divide by 12.9 ohms, what do you get? 0.860. Okay, and that's a little ways from 0.857, but that's we've got some had some round off in there with that 11.1, so should be okay. So the only thing is, let's say that someone, maybe I should make one last page on this. You have to be careful. I think we are at page number 8. Our final thought here is if you've got some sort of a circuit, maybe you've got a resistor hanging out here, and then you have a resistor here, and they talk about the Thevenin model of this. If they ask you for the Thevenin model on this, a good question is, do I include that resistor or not? Okay. Am I trying to come up with a Thevenin model that has that resistor, or am I trying to come up with the Thevenin model that does not include that resistor? So the question is, are you trying to build the Thevenin model of this, or we're trying to model this, and this would obviously just be some other circuit elements, or are you trying to build the Thevenin model for this? Okay. So when they do something like this and they ask you for the Thevenin at these terminals, you have to ask, am I to include this resistor or not? Now, if you don't include this resistor and you build this model, is there a quick fix to get back to this? Yeah, absolutely. If you take that resistor and you put that resistor between these two terminals here, that will take you back over to that model. So it's not a big deal which one you do. It's a communication issue. Which one are they wanting you to do? So if I give you a test question or a lab question or something, I'll try and be very specific. If we say build a model for this R6 or something, we're probably wanting this. If we want the model including that, then we probably want that. So just something to think about in terms of what people say and what they ask for as we wrap up this section on the Thevenin equivalent circuit and the Norton equivalent circuit, maximum power, and things like that. So our next venture will be into operational amplifiers, which is going to be a lot different subject. It's going to be a subject that requires us to really have a good handle on node analysis. So if you're still struggling with node analysis, practice, 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 and we'll get together then. Take care till then, and thank you for watching.